So welcome back. Today in the afternoon session, we will have talks by Professor Raju Venugopalan. As you know, Raju has done so many fundamental work in the understanding of QCD matter, from the initial states of heavy ion collision to chiral anomalies and many more. And you will hear a lot about him from his lectures about these. And the first lecture is like a colloquium. So it will introduce you to the field, and this will give a broad overview of where we stand in terms of understanding the initial states of QCD matter. And Raju, apart from being an excellent researcher, is also an excellent teacher. So I would request more questions from the students that will make this session more interactive. Thank you.
Thank you. So can you hear me at the back? Can you hear me at the back? Okay. Yeah, so thank you very much. So it's a great pleasure being here. So I actually lectured at one of the very first ICTS schools, even before ICTS existed. And that was in 2008, and it was a school that was organized by myself, Rajiv Gavai, Sayantan Gupta, and Francois Gelis, and it was in Goa, right on the beach. So, but it's nice to actually be in the actual physical facility, which is this beautiful campus here, and to give these lectures. So I'm going to give a series of 4 lectures, as you know, and here's the outline of my lectures. So I put it actually very simply here. There's a plan in the U.S. and some nascent plans in Europe to build an electron-ion collider. And the electron-ion collider, if it's built, will be the only existing collider facility in the US since the Tevatron closed down. And the estimated cost for any such machine is on the order of $1 billion. And the question is, why should one spend this money? Okay, so if you want to try to explain to your colleagues, you know, why should you spend this money? That's a useful thing to know, and what I'm going to present is a kind of general science case for that. And a lot of it in this talk, so it's not really necessarily about the initial stages of heavy ion collisions, but it's more a general plea for why QCD is an important field in its own right and deserves this kind of attention in terms of public expenditure. And in this talk, you'll all be very happy because you'll be at a level where you'll understand everything. So you should just relax and enjoy seeing all the things that you know. And if there are things that you don't know, feel free to ask me about them, and I'll try to answer, or I'll try and fudge and run away from you. So that's the first talk, and I think it's also a useful talk in the sense it'll set in context some of the lectures that you've heard, and that'll also be addressed in the next talk, where you heard this beautiful set of lectures on perturbative QCD and its great successes and its power. And also you've heard talks on Lattice QCD and its great successes and its power. And so you can say, well, what's there left to do, right? And so what I'm going to make a case is for what we don't know, given these benchmarks, and why that's important. Okay, so and I think that's really one way to view these first 2 lectures. And then in the last 2 lectures, I'm going to get down more to brass tacks and really describe how, within a particular framework, you can calculate things that people never thought were calculable, okay, for a long time. And you can make predictions and compare to data and so on. And this is a way of thinking about QCD, which is more in line with, you know, cosmology or condensed matter physics, rather than as a precision science to discover physics beyond the standard model. The idea is to uncover emergent phenomena within the standard model itself. So the analogy is that suppose you had QED and you were able to compute G minus 2 to 9 decimal places or more, right? Is that all that is about QED? Okay? And surely not. The whole field of condensed matter physics is QED. And it relies on ideas and emergent phenomena that have come back and influenced particle physics. Okay? So there's a different way of thinking about physics, which is not purely reductive, but also sort of bottom-up, in the sense that there are emergent phenomena which are not apparent when you write down Lagrangian and you compute something to some order in perturbation theory. And so I think that's the spirit within which this talk, or the set of talks, is embedded. So without further ado, so here's the talk, which will be my first lecture, and that's about essentially the essence of matter. It's about imaging matter below 10 to the minus 15 meters, or Fermi, with an electron-ion collider, and all the things one can learn from that. So why is this important? Well, it's important because it's been a historically successful way in which we've learned about the structure of matter, starting all the way in the 17th century, and perhaps even before, with just light microscopes, where one discovered that you had bacteria, right, and you had cellular structure in matter, and then sort of the tremendous advances in the 20th century with, again, using electrons instead of light to look much further down into 10 to the minus 12 meters or so, with very high resolutions to study the properties of materials, right? So, and there was a Nobel Prize awarded for this. This was before Nobel Prizes were awarded. Else surely it would have deserved one. And then there was the era starting in the 50s and 60s onwards of electron accelerators on fixed target machines at highly relativistic energies of many GeVs. So at SLAC, for example, it was around 20 GeV, hitting fixed targets and looking at the structure of matter at very small distances. And so here's the cartoon of what this machine was actually doing, where you had electrons scattering of protons and nuclei, and then probing deep within these at wavelengths of now very small distances, right? Almost unimaginably small distances of about 10 to the minus 17 meters, and similarly small resolutions. And this also resulted in the award of Nobel Prizes. There was a Nobel Prize awarded to Robert Hofstadter at SLAC, and also later to Friedman, Kendall, and Taylor for the discovery of quarks in deep plastic scattering. And then finally, there was sort of this Uber collider, which was different from all of these machines, because unlike these machines where the target was at rest, here you had the protons accelerated at very high energies of almost a TeV, about 900 GeV, maximally scattering of electrons with about 27.5 GeV at very high central mass energies, looking very deep within the substructure of the hadron with extremely small wavelengths. And it's in this spirit that one wants to build the IC and possibly an LHC in Europe. That's a Large Hadron Electron Collider. The EIC is a project in the United States. And you can ask, well, reasonably, why such a machine? Okay? And that's something I will get to. So here's the science case for an EIC, which, it's a science case that we as QCD physicists would have to present to the external community to say, why is this interesting and important? Why should we do this? Okay? And as I said, there's a lot of it that you will know and feel familiar with, and that's good. And I hope there's one or two things that you will not find familiar. And so you can think of it as a story of origins, because that's what it's about, right? Where does the mass of the visible universe come from? But more specifically, you can couch it as, what is the essential mystery? Okay? What is it that we really want to know? Okay? And when you say that, you have to couch it in the context of what we already know, okay? What we would like to know, and how to get there to address these fundamental questions. Okay, so think of it as a play in 4 acts. And Act 1 is that of the mysterious gluon. So here's a chart of matter and the force carriers of the standard model that is on every physics hallway in the world, hopefully. And here's the gluon. And if you talk to many of your colleagues in other fields of physics, they don't even know about gluons, actually. You would be surprised about, a lot of people heard about quarks. Quite a few have heard about the Higgs boson even, and neutrinos. But very few have heard about the gluon, which is, in that sense, a humble object. It has very simple quantum numbers. It has no mass, no charge, and a spin 1. But it's the force carrier of the strong force, okay? Which is the strongest force in nature that we know of. And as such, is a fundamental building block of the standard model. And you heard today, in this beautiful talk in the morning, about the discovery of the gluon. Okay? And in fact, and rightly so, it was stated rightly so, it was really the discovery of the gluon that really convinced people that QCD was the correct theory of the strong interactions. It was the final nail in the coffin of alternative ideas and suggestions. Okay? And that was as a result of these experiments at the positron-electron ring accelerator at DAISY in Germany. And this is specifically in the Tasso detector, where they discovered 2 and 3 jet events, and the 3 jet events were the ones that really gave unambiguous evidence for the existence of gluons. And as you heard this morning, that one was subsequently able to also really learn about its intrinsically non-abelian nature and put constraints on its mass as well. So this was really something that was a landmark event. Unfortunately, it hasn't received a Nobel Prize for complex reasons, but it's perhaps still not too late. So here's the essential conundrum, if you like, and you can think of it as a cosmic koan, okay? That quarks, which we know get mass from the Higgs mechanism, really give you a very small fraction of the mass of visible matter. It's only 1 to 2% of its mass. Okay? So that's what the Higgs does for you. Yet, we are about 100 times more massive. I mean, the proton and the neutron are about 100 times more massive. And their mass really comes from the dynamics of quarks and gluons. And gluons play an absolutely critical role in this. So they're responsible for the mass of visible matter. Okay, so in fact, this is so striking a difference to what is presented in popular lore that makes some people really mad. Okay, but in fact, this kindly person, quite a contrast, when he was thinking about the Higgs boson, right? He was actually really not sure at all it was relevant at all, and he was actually thinking of this as a way to solve confinement. Okay? So introducing these scalar particles to confine quarks and gluons. And that really wasn't successful, but it led to something else. In fact, in a splendid irony, it's actually the fusion of gluons, which is the dominant process for the production of the Higgs, and it's decayed to various channels at the LHC. So the story kind of continues that way. Now, of course, I think someone said that every talk on QCD has to have a plot of the running of the coupling with the momentum transfer. But you know, it's good to stare at things that you know very well sometimes. And what was really remarkable about this was that in QED, we know that when two electrons scatter off each other, they can emit photons, which will then go into some electron-positron pair, which will screen the charges between the electrons. While what is really unique in QCD, as you all well know, is the self-interaction of the gluons. And that has a different sign from that of the quark loop here. And that's what it's the fact that this is much larger, which leads to this decrease of the coupling with momentum resolution. Now, the other side of the coin, and that's sort of beautifully represented the wisdom of our organizers in the two sets of talks that you've been seeing, is the opposite of asymptotic freedom, which is infrared slavery, okay? Which was a term, I believe, coined by Howard Georgi, where he argued that the fact, I mean, people at that time, you know, couldn't understand why quarks and gluons weren't visible in nature, and it took some wisdom to realize that it was a feature, not a bug, of the strong interactions. Namely, that when you try to take quarks and gluons and split them apart from each other, the force between them, as represented by this potential as a function of r, I believe Peter showed this plot. This potential grows linearly with the distance, with a value that's proportional to string tension. So, in fact, one can show in this kind of simple picture that quarks, which are on the size of 10 to the minus 18 meters, experience a force about 16 tons at a distance of 1 fermi. So, okay. And so, you know, one can try and sort of build pictures, simple pictures, where you think of quarks as these rigid rotors with some string tension, which is proportional to, which is given by the sigma. And remarkably, these kinds of pictures let you understand things like radio trajectories, which are where you plot here the spin of mesons as a function of their mass. Okay? And you can understand these kinds of trajectories as excitations, okay, of this rotor. Because of the angular momentum of these rotating quark-antiquark pairs, and you see that they lie on these beautiful trajectories, okay, which is very much consistent with such a picture. But we know this is not true, as I believe Peter also mentioned, because we know that in QCD that these strings break when you pull them apart. So it's clear that this picture, even though so simple and beautiful, must not be quite right. Okay? And there are lots of such examples in QCD where there's some beautiful physically intuitive picture. It explains certain patterns and data, and then you go and apply it to something else, and it falls on its face. So here's the essential mystery, okay? That we know that all visible matter is made up of quarks and gluons, okay? But they're not visible themselves. Okay? And that's not, as I mentioned, not a bug, it's a feature of the theory. So that's really remarkable. And then all strongly interacting matter is an emergent consequence of many-body quark-gluon dynamics. And this explains the fact that even though the quarks themselves have very little mass and gluons are massless, they're able to generate the masses of protons, neutrons, and other subatomic particles. And from these kind of patterns that we see, radio trajectories and the behavior of cross-sections and so on, you see that there's an elegance and simplicity to this strong force that we don't understand. Okay? So we can calculate a lot of things, but it doesn't mean we understand things. Okay? And so what I'm trying to get at is that the fact that you have this big elephant in the room, confinement, is really a fundamental problem in theoretical physics. It's one of the most profound problems of our times. It explains why we exist. And it's something that, despite a lot of work, we are just a little bit further towards understanding. Now, you can give up, like a lot of people, and try and do string theory or something like that, right? Which is perfectly fine. Okay? But I think, at the end of the day, solving problems in physics need empirical tools. Okay? And the wider the range, okay, and versatility of your tools, okay, allows you to have the potential for fundamental breakthroughs. And this is a problem that deserves a fundamental breakthrough because it's one of the most profound problems in all of science. The problem of confinement and how quarks and gluons actually get mass, and some understanding how that happens. So that's Act 1. Okay? But as I said, before we get to thinking about some of these other issues, let's address, and revel in the power and the glory of quantum chromodynamics. And this had very humble origins. It came from a miasma of confusion. And as you heard today, Gelman and Zweig, with his aces, were playing around, futzing around with trying to organize, the newly discovered subatomic baryons and mesons into octets and decaplets and so on, and trying to understand them in terms of new quantum numbers. And at that time, quarks were thought of as some kind of a abstract fiction. Okay? People weren't really sure that they actually existed, okay, whether they were real or not. And it took a long time, the discovery of color by Nambu, and really understanding the spin statistics associated with these new internal symmetries, which really, it was like how an ugly pupae becomes a beautiful butterfly, going through this very kind of almost mysterious process, ultimately resulting in asymptotic freedom and so on. So it was actually a painful and quite illustrative way in which how science progresses. But now, of course, we just stand here and look at this, and we're very happy about it. But, anyway, so this was a lepidopteral metaphor for how QCD came to be. But it is really something special. Okay? And why is that so? Because it's nearly perfect. Okay? There's this song from Mary Poppins where he says, "You're practically perfect," right? So it's nearly perfect. And that's very unusual, actually, in our theories of nature, because lots of theories have lots of parameters. Okay? And especially if you work with various kinds of effective theories that physicists worked on in the past, you're always working with lots of parameters playing around. Okay? And if you take the quark masses to 0, right, the theory QCD has no parameters whatsoever. Okay? But the other thing you see is that the theory is very rich in symmetry. And as C and Yang taught us, symmetries dictate interactions. So just understanding the richness and variety of these symmetries allows you to understand the interactions in the theory. And these are several, right? So you have SU3 color, okay, which is a gauge symmetry. Okay? It's a local symmetry which is unbroken but confined. Okay? So you never see color in nature. There are no free quarks and gluons, or color charge more generically. It has a chiral symmetry. Okay? So left and right-handed quarks, okay, can be thought of, in the case of massless quarks from the Lagrangian, as being independent degrees of freedom. And that's exact for massless quarks. That's a property of the QCD Lagrangian. That it has baryon number and axial charge, which are conserved for massless quarks again. And then also the theory is scale invariant for massless quarks, gluon fields, and then it also has discrete CP and T. But what is perhaps even more interesting than this whole plethora of symmetries is the fact that they're broken in interesting ways. Okay? So the chiral, axial, scale, and principal P and T are broken by vacuum or quantum effects. And that's what actually is responsible for existence. So it's this beautiful fact that you have this incredible symmetry, but then it's the slight breaking of these symmetries which actually is responsible for the mass of matter and the existence of our visible universe. And one of the things you appreciate when you think about this is that inherent in QCD are the deepest aspects of our understanding of nature, our modern understanding of nature, which is that of relativistic quantum field theories. And these are confinements. Like who would have imagined, that you could have objects which are elements of your Lagrangian but are not visible in your physical spectrum. Okay? That's QCD, right? Asymptotic freedom, that charges become weakly interacting as they get closer and they get more strongly interacting larger distance. The phenomenon anomalies, okay? That the fact that the measure of your path integral can have observable consequences, for example, the decay of pi naught to 2 gamma. Okay? That's really fundamentally coming from the non-invariance of the measure of your path integral to this UN axial symmetry. And then also the spontaneous breaking of chiral symmetry. The fact that these left and right-handed quarks, which are like independent objects or massless quarks in your Lagrangian, they get kind of tied in lockstep, okay, with anti-left-handed quarks bound to right-handed quarks to form a condensate, which gives us mass, okay? Or at least is one element of giving us mass. So, yeah. No. Well, so CP turns out to be a good symmetry for QCD, but this is that you can have metastable states in QCD, so QCD in principle could have something called a theta term, okay? And that's related to the axion that you might have heard of. And so, so there are bounds on explicit CP breaking terms in the QCD Lagrangian, with this theta term being less than 10 to the minus 9. However, there are vacuum effects in the theory, okay, which can lead to metastable states that break CP. Okay? And if I get a chance, I'll talk about this in my last lecture. So here, okay, so one can take a bloody-minded view and say, well, you have QCD, you claim this is your theory. Why don't you just put it on a computer and solve it, right? And this is what Peter was telling us about. Okay, so and here's the guy, Kenneth Wilson, who sort of came up with this idea, and he's holding a telephone, if you recognize that, and these are computers. Okay? So that's what probably unrecognizable now, but anyway, so Lattice QCD, which is one of the reasons why Wilson was awarded the Nobel Prize, is really a fundamental way of thinking about QCD. Okay, so because as we know, again, right, in relativistic quantum field theories, it's not meaningful to think about such theories without the idea of regularization. Okay, that it's fundamental to the nature of the theory that you have infrared and ultraviolet regulators, and the best way to think about these is a lattice. So if you have any problem in quantum field theory and you want to understand it deeply, try to put it on a lattice to really understand what's going on. So this is really a deep concept, and the lattice has been enormously successful, as we heard from from Peter, specifically in the context that he mentioned of finite temperature and baryon density. But in general, it gives a first principles treatment of static properties of QCD, masses, moments, and thermodynamics that Peter talked about. But it's still, you know, as you probably gather from Peter's talk, it's even for those quantities, it's a formidable computational problem. But it's absolutely challenging for dynamical processes. Okay? So there's been some recent progress in trying to understand scattering and so on in Lattice QCD, but it's a very challenging problem. So if there's ambitious people among you who want to win a Nobel Prize someday, you know, sort of start thinking about this problem. Because I mean that's kind of the nature of this problem. And so here you kind of have this conundrum. So you have this beautiful kind of formulation, but it's challenging for many things. But again, this is about the power and the glory, so let's celebrate. So if you look at the lattice now, it's reached a level of precision that's really quite remarkable to behold. So these are the masses of the various hadrons, okay? And they're compared to experiment, okay? And with just a few inputs, those are the ones shown in blue here. Okay? So that's the kaon and the cascade, and the sigma, sorry. You find that you can reproduce to very good accuracy the masses of the hadrons. This is the best evidence that QCD, well, until 2009, it was the best evidence that QCD is the correct theory of the strong interactions. But you can actually even do better, which is now you can not only look at the masses, but you can understand mass differences in QED. So note the difference in scale in the two cases. So here it's in the hundreds of MeV differences between the different hadrons, while here it's in a few MeV differences. And so this is the difference between the different multiplets of nucleons, sigmas, cascades, and so on. And what people have succeeded in doing is putting both QED and QCD on the lattice, which you need because there's an electromagnetic contribution to the splitting between the mass of the proton and the neutron, for instance. Okay? And so you need to take that into account. And so you see you get that with very high precision. So Lattice QCD can make few MeV level predictions, sort of comparisons, but it can also make predictions. Okay, so these are actual predictions that were made. Okay, and you see that it's actually really quite remarkable. So there's actually no data for this object here, so it actually constitutes a genuine prediction. And there's actually a relation between the masses of these, the delta n, delta sigma, and delta chi, which is called the Coleman-Glasher relation, and it's predicted to be 0, or sort of close to 0, but you know, you actually get something slightly different, and this is an indication of flavor symmetry breaking in QCD. Now, I should also talk about deep elastic scattering. So you heard in quite some detail about this, so I won't belabor the point. And so in deep elastic scattering, as I mentioned, you're studying the internal structure of the proton at very high momentum resolutions and values of Bjorkane X, where this Bjorkane variable, which is an invariant in the scattering, is a measure of the momentum fraction of the quarks that are inside the hadron. Okay? So you can write down the cross-section for an electron to go into the final state of an electron, and all kinds of stuff, right? Hadronic stuff can be written as the product of the Rutherford cross-section, which is the alpha electromagnetic over q to the 4th, right? So it's suppressed by the momentum resolution here. So it goes as sine 4th theta over 2 here, times the structure functions F2 and FL, which are themselves indicative of where F2 is indicative of the sum of the quark and anti-quark distributions inside the proton, while FL is directly proportional to the gluon momentum distribution inside the proton. Now, so as you know, this program was a great success. So from the SLAC fixed target experiments that I alluded to earlier, you found that in a certain kinematic region, you saw that F2 was independent of Q squared. Okay, so in principle, it's a function of X and Q squared, but in this kinematic window, they found that it was really some universal function of X, which suggested scaling of distributions. And this is actually quite remarkable if you think about it, because people thought that the strong interactions were strong, right? So the objects inside the hadrons should be very strongly interacting. And so this came as a complete shock when people discovered that this data is being explained by essentially non-interacting quarks inside the proton. Of course, we now know that that's because of asymptotic freedom, but at that time, it was really quite a big surprise. And here's the plot that was alluded to as the propaganda plot, okay, for deep elastic scattering of F2 as a function of Q squared. And this is data from Hera. And what's remarkable is that this is almost 5 orders of magnitude in X. So you're looking at momentum fractions carried by the quarks inside the proton, which are 100,000th the momentum of the proton. Okay? And very, very large resolutions, right, going to 10 to the 5 GeV squared. And if you compare this to the SLAC experiments, you see the SLAC experiments sit here. And so what Hera did was really open up the phase space and also really tell us that QCD is really more than just scaling, that it has patterns which are well explained by detailed comparison of theory and experiment, as you heard today. And from this data, you could extract the picture, which also was something that people didn't anticipate, is that the proton at high energies is really not just a simple object made out of 3 valence quarks. Right? It's a complex many-body system. And if you look at this plot, this is the distribution of gluons and C quarks inside the proton at a fixed resolution Q squared versus X. And this is telling you about the number in some picture of the number of quarks and gluons inside the proton at high energies. And it's clearly not small, it's a very large number. Okay, so it's telling you that at very high energies, the proton fluctuates into a state which contains not just the valence quarks, but a large number of gluons and C quarks. And this object is no less the proton than it is a proton, which is that of 3 valence quarks. Okay? So that picture is all hidden here, while this picture of the proton is containing states corresponds to this big picture here, where you have the proton fluctuate into this large number of gluons and C quark pairs. So the remarkable success of QCD, right, or what we call perturbative QCD now, was that you could use this data and extract these parton distribution functions, as you learned for the last few days, and compute things in hadron-hadron scattering. So this was an electron-proton scattering from Hera. These are the parton distribution functions. And these parton distribution functions could be used as inputs into the calculation of, say, jet cross-sections. So this is data from RIC, the Tevatron, and at the LHC for a range of what are called rapidities. These are logs in X, roughly. And so you see beautiful agreement across many, many orders of magnitude. And so at very large momenta, the weak QCD coupling enables systematic couplings, derivation of factorization theorems, and so on, which allow you to make this thing. So we look at this and we're kind of blasé about this, but this is really a tremendous collective success of the field of thousands of people working over tens of years to achieve this. So, the power and the glory, right? So QCD works. It's the correct theory of the strong interactions. So it's appropriate, and some of our colleagues in other fields may ask this, is that are we done? Okay? So we have, so this is actually These are words from Frank Wilczek at a talk he gave at the Quark Matter Conference about 5 years ago. And he said, and it's worth quoting, he said, the study of the strong interactions is now a mature subject. We have a theory of the fundamentals, QCD, that's correct and complete. In that sense, it's akin to atomic physics, condensed matter physics, or chemistry. The important questions involve emergent phenomena and applications. Now, some people may say, well, we are done, okay? But if you were to say that, you would empty all the physics departments in the world very quickly, right? There would be no condensed matter or atomic physicists so try saying that to them, right? So they're not going to be very happy if one had that perspective alone. And I think that was partly the point that Wilczek was trying to make. So it's then important now to step back and say, what is it that we actually don't know? Okay, so what are the frontiers of our ignorance? Okay, we usually talk about frontiers of knowledge. So what are the frontiers of our ignorance? So let's kind of try and put that all in one plot. Okay, so here's the landscape of the strong interactions. Okay. So here, and I've done it in the language of deep elastic scattering, which is one of the simplest processes in which to think about QCD. So that's in terms of the resolution, which is Q squared, and the wavelength, or the energy, which is 1 over Yorkian x, right? So this is like the first slide I showed you of the light microscope, right? Looking into the structure of matter. There was resolution and wavelength, right? That's what I'm plotting here. So what is it that we really know? Okay, so at very high Q squared, okay, which is part of the total correction in high energy, we understand this very well, okay? We know that perturbative QCD works. It has tremendous predictive power, and it's the benchmark for looking in collider experiments of physics beyond the standard model. Here, this very non-perturbative regime of strong coupling, so this is weak coupling and this is strong coupling. So this is the asymptotic freedom line here, so you're strong coupling or weak coupling. So here, this is very non-perturbative, right? And that's where the lattice comes in and really helps out, because you can put QCD in a lattice and at least you can answer some questions about the masses and moments and mass differences between the different hadrons. But it only works for static quantities. So if I'm doing low energy scattering in QCD, I'm still at a loss. Okay? But then you can think of effective theories like chiral perturbation theory. So chiral perturbation theory actually is QCD in the low energy limit, as Weinberg has argued. And you can make some progress there. So this sector, you can say, well, we kind of know something here. But then what about all of the rest of the stuff here? Okay? When you do high energy scattering experiments, the bulk of the cross-section is at small momentum transfers, but at very high energies. And there we have effective descriptions in terms of objects that people have been talking about since the 60s, like pomerons and regions and so on. But we really know further now than we were then, okay, in trying to really understand them. When you start going away from this very high Q-squared regime, there are power corrections that become very large, okay, and this is something that people don't talk about as much. Where you get so-called higher twist corrections, which I think is a terrible, terrible word, okay? I mean, to a condensed matter physicist, higher twist corrections are what are interesting because they tell you about many-body correlations, okay? When you look here, what you're talking about are one-body distributions, okay? So you go and tell a condensed matter physicist, hey, I learned a lot about one-body distributions. And they'll say, this is not interesting at all. I want to learn about the correlations. I want to learn about many-body correlations in your system. Okay, so if you want to understand that in a controlled way, that's still completely unknown. And as I'm going to talk about, there's an interesting regime where the physics may still be weak coupling, but it's completely non-perturbative. Okay? So usually when you think about coupling, weak coupling, you think perturbative physics, okay? But that doesn't have to be the case at all. You can have weak coupling, but very, very large occupancy. So if you think about cold atomic gases, for example. There's a regime where the coupling is very weak, okay? But the interactions are very strong because you have a large number of these atoms, okay? So the effective coupling is the coupling times the number of these atoms. So there's a similar regime at very high energies in QCD where you have very strongly interacting matter even though the coupling is weak. And that's actually very interesting, and I'm going to say something about that. Okay? So here's a summary, right? So perturbative QCD is beautiful, right? And works, but it only describes a small part of the total cross-section in the strong interactions. Lattice QCD is very powerful, but of limited utility, especially in dynamical processes. Effective theories work in different regimes, and that's one big way to make progress, and a lot of the rest of my talk is going to be about a particular effective theory. But again, there are questions about how to use these effective theories, okay, in a way that you can actually learn something fundamental about the strong interactions. So that's kind of, so if you could take a very different perspective and say my Act 2, which was all about the success of QCD, was all limited to small corners. But these are important corners, okay, of the strong interactions. But the vast bulk of phenomena are not understood fundamentally in QCD. For example, okay, let's take the simplest possible example. So if someone comes to you and tells you, hey, I really understand QCD. I went to the school, in Bangalore, and I was closeted with 30 other kids, and I learned everything about QCD. I'm done. Okay? Let me learn something else. So someone could come and say, okay, tell me, what does a proton look like in terms of these quarks and gluons you've been telling me about? Okay, does it look like this? Are there gluons with these quarks rattling around the bag? Or do the gluons cluster around the quarks? Or do we have these kinds of, boomerang or Mercedes star kind of shapes that some lattice gauge theorists tell us about? Which of these is? And then if you say, well, I really believe the lattice, and the lattice tells us it's this, okay? Then you can say, well, okay, now what happens if I take my proton and I boost it to high energies? What does it look like? Okay, does it still look like this, or does it look like any one of these pictures? And these are dynamical questions that we don't really know the answer to. So these are such basic questions, right? If someone in a different field came and told you that they understood what was going on, you would expect them to be able to answer such questions about what is the structure of matter. In fact, let's look at an interesting example, which is what happens when you boost protons. So think of you're a proton and you're sitting at rest, okay, and you're made up of 3 quarks. But even if you're these 3 valence quarks which are chugging along, they're moving very slowly, right? We know from QCD being a relativistic quantum field theory that there are always these virtual fluctuations of gluons which are exchanged between these quarks and can fluctuate in and around the vacuum around a single quark. Now what happens at high energies? Okay, when you boost the hadron, what happens is that these fluctuations, they start to live longer and longer, right? You have time dilation. So all these things start to live longer and longer. And now if you come and hit it with a hammer, right, which is your electron at some q squared, what you're going to see are not very few of these objects, but you're going to see a large number of gluons. And these can further split into quark-antiquark pairs. And that's what explains this plot here. So this plot is a fluctuation on a very small time scale, okay, of the hadron into a very large number of constituents which you happen to probe on that short time scale. So you can ask yourself, okay, what happens if I keep boosting further and further and further and further, okay? What happens, okay? So does this keep growing and growing and growing? Okay? And is it, what happens? Is it like a popcorn machine? I'm trying to kind of fill it up with kernels of popcorn, and at some point, am I going to blow the lid of the proton when I do this? Okay? Or is it going to stay just as it is somehow miraculously? Okay? How does that happen? Anyone know the answer? You understand QCD, right? We don't really quite understand the answer to that. In fact, there's some remarkable predictive phenomena which go under the name gluon saturation, which tells you that as you take a proton and you boost it, so here I'm boosting it now in energy this way, and if you're an electron and you're seeing the proton coming at you, then as what's happening is that these quarks and gluons inside are getting denser and denser and denser and denser, okay? And at some point, what happens is that the gluons, they start to feel each other in phase space. Now, gluons are not like photons. They don't all go and sit in the ground state. They carry charge, unlike photons, right? Gluons carry color charge. So they start repelling each other and strongly interacting. So that's many-body physics, just like in condensed matter, okay? And so it's predicted that what actually happens is that there's an emergent scale, okay, which as you go to higher and higher energies becomes a larger and larger scale. So you start screening color at smaller and smaller distances inside the proton. So naively, you would have thought that the proton screens color on the scale of lambda QCD, okay, but in this very high energy limit, you might be required actually to screen color at shorter and shorter distances. And that's emergent dynamics. Okay. And there's a picture again of this plot of now I plotted x, or energy on this scale, and q squared, or resolution on the other, which tells you how this dance of partons happens in this landscape. And it also, and I'll describe this in my next lecture, the scale also grows with the nuclear size. So if you have a larger nucleus, yeah. How do I know that the gluons will repel each other? So I'll discuss this at length in my next lecture. It's actually a very good question. It's actually a dynamical phenomenon. Okay, so it's something that's not something you would predict on the basis of the Lagrangian. Again, it's an emergent phenomenon. So you actually see it when you do so-called higher twist calculations. It turns out that there's a delicate cancellation between attractive and repulsive interactions, which gives you a net repulsion, okay, in the theory. But one can understand this in many different ways. I mean, one way to think about it also is that the gluons or the fields, gluon fields, can have maximal occupancy in the theory. Okay? And so there's a attractive, so Bremsstrahlung to produce more and more gluons is attractive. It's an attractive phenomenon, so you produce more and more soft gluons. So you know that at some point you have to have some maximal phase space occupancy in the theory, which is 1 over alpha s. On very general grounds, you can argue that you have a maximal phase space occupancy. And that must necessitate that something resists this Bremsstrahlung to the ground state of zero momentum gluons. So if everything went and sat in the ground state, you would have a condensate of color in QCD, which is forbidden. Okay? You would break SU3 color. Okay? So there's many ways to think about this problem, and I will discuss this at greater length. It's a good question. It's absolutely not obvious that that's the case. So this is your question. How does this happen, right? What are the right degrees of freedom? So the question is, when you get to this regime, is it even reasonable to start thinking about gluons or partons anymore? Okay? These are just strong fields. Is there a fixed point for this kind of RG evolution as you go up in this landscape? How does the coupling run? Does it run as a function of this emergent scale? If it's a larger scale in the problem, okay? Are there other scales? And how does this phenomenon transition to chiral symmetry breaking and confinement? So there's a whole set of questions which are analogous to the kind of questions that many body physicists thinking about universality and renormalization group kind of evolution of many body correlations would ask. Okay? And I'm claiming that in QCD, there's an entire sector of the theory which can be formulated most efficiently in terms of such a description. Other than the conventional description that one has for one body distribution, there's an entirely different paradigm for understanding this structure of the theory, which is closer to what your condensed matter or cosmology colleagues would think about. And so one should open one's minds to this possibility, and my other lectures will actually explore in some greater length this kind of perspective. And so it's a new frontier. Okay? We don't know much about it. And the conceit is that now I've plotted resolution, nuclear size, and energy. So a lot of physicists working in perturbative QCD don't want to think about nuclei, like they don't exist. Okay, like these are not also objects which are made up of quarks and gluons. And at some level, when you go to start probing nuclei, you want to understand, just like you understand different condensed matter materials, what are the universal features of this theory of the strong interactions that are universal across different strongly interacting systems? Okay? Is there a regime where I'm going to see a certain kind of dynamics that is independent of the nature of the valence distributions of quarks in that system? And so one could ask a question that if you now open the window of nuclear size, is there going to be a new regime of dynamics which is universal, okay, across different nuclei? And finally, as I argued, and I will argue further in my next lectures, this is a regime of very strong fields in QCD. Does that give you a window to understand confinement? Can you sneak up to confinement through the back door? Okay? So we've been talking about confinement, strong fields, and it has this mystical aura about it, okay, that only Lattice can talk about it and so on. But, or we sort of put it into nice little boxes and forget about it. Okay? But the question is, can you understand strong fields and weak coupling at sufficiently high energies and try to understand the systematics of that and whether that mimics the systematics of another strong field regime, which is the confinement. And so there's a whole set of issues that comes about when you start thinking about the problem this way. Now, here's another thing that if you go to your friends and tell them you understand QCD, so besides asking you, well, what does a proton look like? They can say, hey, you know, I heard that protons have the spin 1/2. And you guys tell me that the proton is made up of all these quarks and gluons, right? So how is it that all these quarks and gluons somehow add up to 1/2? Okay? So I have this spin 1/2 of the proton, but you know, I have quarks, and the quarks also have spin 1/2, and gluons have spin 1, right? So if you say that the proton is made up of quarks and gluons, as you claim in your QCD, explain to me that how this works, okay? So anyone know the answer to that? So this was actually an object of investigation for a long time. So there were beautiful experiments done at CERN with electron and muon beams on fixed targets, and also at SLAC, where they tried to precisely address this question. Okay, so they looked at polarized targets, polarized protons, and they did deep elastic scattering experiments. And what these experiments discovered was that the quarks, so here's a plot, here's this cartoon which shows that 1/2 is being possibly due to the spin of quarks, spin of gluons, the angular momentum of quarks and the angular momentum of gluons. Some combination of all of these, which gives you the 1/2 of the proton. And so these fixed target experiments show that the quarks carry only about 30% of the proton spin. And so this was a big crisis. Okay? And again, like a lot of things in QCD, like I alluded to before, it's something that just fell flat on its face. So there was something called the quark model. Okay? And when I was growing up, it was still a big deal. Okay? But I'm a lot older than you. Okay? And people understood all this amazing spectroscopy of hadrons. So people did all this kinds of hadron spectroscopy at different levels, just like nuclear physics. And they were able to explain a lot of it based on this very simple quark model. Okay? Of relativistic quarks in this bag of fields. But then when it came to spin, it just breaks down completely. Okay? Because the quark model would tell you that this fraction would be much larger. It would be about 70%. So it's clearly not right. Okay? So the experiments completely rule that out. So this tells you that this picture of relativistic constituent quarks so you have 3 relativistic quarks and then they add up to give you spin 1/2. That's just wrong. Okay? So we know that we have to look further. And However, there are no more experiments on fixed targets and deep elastic scattering. What we learned now is the next stage of what we learned about the spin of the proton was some experiments at RHIC, at my home institution, Brookhaven, the Relativistic Heavy-Ion Collider, where they collided polarized protons and polarized protons. It's not as clean as polarized electrons and polarized protons, but they were still able to do beautiful experiments, very challenging experiments. And from that, and using perturbative QCD, they were able to conclude that actually gluons carry some spin. So what's plotted here is delta G, okay, which is the is a shorthand for the spin of the gluon, as a function of x integrated over x. So this is the integrated spin as a function of x, but it's integrated from some region which is very low x to 0.05. And here's the available data, okay, from 0.05 to 1. So this is data from RHIC. And they were able to conclude, so this was the kind of the initial uncertainty in the spin of the gluon. It was all over the place. It could be as large as +1 or -0.5, okay? So all over the place. But what the RHIC experiments did was to shrink this window of what the spin could be, and this is the most likely value, okay, suggesting that it could carry 20 to 40% of the proton spin. But there's still this huge uncertainty here because the experiments at RHIC could only go up to a certain energy. So this is the, in some sense, the energy uncertainty in knowing the spin of the gluon, which is quite significant. Okay? So we don't know, again, what the spin is carried by the gluons. We don't know what the angular momentum is. Okay? So these are things about basic things, right? That if you think about classical physics or you think of other areas of physics, you kind of would ask these questions about. Now, again, we don't know about the three-dimensional structure of parton distribution. So usually when you hear about parton distributions, they are one-dimensional objects. They're a function of x and the resolution scale of your probe. What's happening with the transverse momentum of the partons inside the proton? And in the last decade or so, there's been really almost 2 decades, but there's really been an explosion in the last decade of studying so-called transverse momentum dependent distributions. And these are, again, you can think of this in deep inelastic scattering, where you can do beautiful experiments where you would measure the electron scattering of a hadron, but then in addition to just measuring the electron, you measure a pion or a kaon coming out, okay? And you measure the momentum of that pion or kaon relative to this q² exchange between the electron and the pion or the whatever meson that you have. And based on these measurements, you can look at a polarized proton or an unpolarized proton, and you can define in perturbative QCD now a whole range of distributions. I apologize for this plot. I hope you can see it. On the y-axis is the nucleon polarization, whether it's up, longitudinal, or transverse. And here's a quark polarization. And so let's take, for example, this guy here. It's called the Sivers function. You could define a KT-dependent distribution, which is the difference between the parton distributions in a transversely polarized proton this way or transversely polarized this way. Okay? And you could measure such distributions. You can also measure something called, in addition to the things like the helicity distributions here, there's a whole slew. This is the one I was looking for, the Bohr-Mulders, where you have now an unpolarized proton, but you look for transversely polarized quarks one way or the other. There's a whole slew of these distributions that one can measure, and these are called transverse momentum distributions. And they tell you about the transverse momentum structure of quarks and gluons inside the proton. That's also something that's new, that we know very little about. You can also do other kinds of experiments, and they generally go under the name generalized parton distributions. And an example of that is something called DVCS, deeply virtual quantum scattering. So where you have an electron scatters off, emits a virtual photon, right, which scatters of a quark inside the proton, and that quark emits a real photon. Okay, that's why it's Compton scattering. Okay, and then is absorbed in the Compton conjugate amplitude. I mean, it's actually, sorry, in the amplitude itself, it's absorbed again by the proton. Okay, and the proton remains intact. Okay, so it's like surgery. So you take out a quark, right, and you hit it with a virtual photon, and then it emits something, and then it goes back into the proton, and the proton goes along. Okay, with slightly different momentum. Right? It's kind of remarkable, right? The proton remains intact, but then you measure a photon and the electron coming out. And this actually leads to a whole set of different distributions, which can be a function of the momentum transfer between the incoming and outgoing proton and the relative x fractions of the quark that was taken out of the proton and put back into the proton. Okay? And these generalized parton distributions are very powerful objects because they tell you about the spatial distribution now of quarks and gluons inside the proton. You can not only ask questions, okay, oh, well, you know, I had some process and something happened at some x. You can say, hey, what was the KT? That's TMDs. What was the, where in the proton was the parton, okay, when it was hit? Or what was the kind of spatial distribution inside it? And generically, these are called Wigner functions. Again, our friends in StatMech and condensed matter physics, they know all about Wigner functions. Okay, that's the bread and butter of what they do. Okay, and so in QCD, we're only now starting to think about these differential things, okay? Which are just in statistical mechanics. It's it's something that people have been talking about since Wigner, right? And so these are really potentially extremely powerful objects in addressing some of the essential mystery that I articulated. Let's go to nuclei now, okay? So I'm still in the frontiers of our ignorance, okay? So this is still Act 3. And so nuclei, okay, so yeah, nuclei are not interesting, right? Just as linear superposition of nucleons, right? What could be new? Well, again, there were experiments done at CERN and at Fermilab and at SLAC which show that that's absolutely not true. So if you look at the ratio of quark distributions in the nucleus relative to that in the proton, as a function of Yorkian X, you find there's all kinds of structure. It's not one. So if it were a superposition of nucleons, it would just be one. Okay? You have things that people have assigned labels to. Okay? When people assign labels to things, they think they actually understand them. Okay? But that's often not the case. Okay? We don't understand it at all. So there's things like shadowing, where the number of quarks are actually less in that kinematic regime times A than what you would expect in a nucleus. Here it's more. Here it's less. Okay? And they have names like EMC effect, anti-shadowing, and so on. And you can again split these into the ratio of gluon distributions, C quarks, and valence. And just look at the uncertainty in the gluon distribution in the nucleus. It's immense. It's all over the place. Okay? And these are from these PDF fits that people do based on the existing data. Okay? So this tells you how little data there is. So to first approximation, we haven't measured the gluon distribution in the nucleus. It's virtually unknown. Okay? I mean, because the lever arm in experiments of nuclei hasn't been large enough to actually make that measurement. There's now first data from the LHC, which promises to be a measurement of the nuclear gluon distribution. So the new nucleus should be thought of as just as different materials in condensed matter physics are thought of, is that they are a laboratory for understanding the collective properties of strongly interacting matter. So if you go to your condensed matter friends, they're all interested in all kinds of incredible phenomena that you see, Hall effect, properties of graphene, so on, strongly correlated electrons, right? Well, here's your laboratory for you, okay? Here's your strongly interacting laboratory. So I can ask questions like, okay, if I now produce a quark inside the medium, how much will it radiate before it forms a hadron? If I form a hadron inside the medium, how is that different from if it were formed outside the medium? Okay? How much does it scatter? This is terra-incognita. We know very little about this stuff, right? So we don't know about the internal QCD structure of nuclei at high energy. So what is the quark-gluon nature of nuclear short-range correlation? So Act 4, okay? So I told you what the problem was. I hope you still remember. It's about the fact that we know nothing, okay? So that we don't know where we come from, that, you know, there's this essential mystery to QCD that we don't fully understand, and that has to do with confinement and some of the emergent phenomena of the theory. And then the second act was about how we actually have some benchmarks which are very powerful and very successful and shouldn't be dismissed and thoroughly appreciated. So that was Act 2, and Act 3 was, you know, just to tell you all the things we don't know, okay, that people in other fields take for granted. And here's Act 4. That's saying physics is an empirical science. Someone said it's not mathematics, okay? One can try and prove that there's a mass gap in QCD, okay? But, you know, it's an empirical science, and you need to exploit all the tools that you have to the maximal extent possible and invent new tools. And so what is the EIC? It's got many firsts, so that's important. Okay? It's going to be the world's first polarized electron polarized proton collider. There's never been an electron proton polarized collider, so it's going to be the very first. It's going to be the world's very first electron heavy ion collider. Okay, we've only had fixed target experiments with very limited lever arm, so that we don't even know what the gluon distribution of the nucleus is, right, like I mentioned. So it's going to be a first for that. Now, the other thing that's going to be really interesting about the EIC is that it's going to be the laboratory for many body physics at different levels, where you measure correlations. I can look at a pion here coming from a gluon, or a bunch of gluons, or I can look at something else coming from a bunch of quarks and look at their correlations. And for that, you need luminosity, okay? Because it's very expensive in terms of luminosity to look at these things. And so what the EIC would have is luminosities of 100 to 1,000 times that of Hera, the design luminosity of Hera. So it would be between 10 to the 33 and 10 to the 34. And it will also have very high energy, so it can also go to very fine resolutions, so quite large Q-squares. And so the electron-proton center of mass energy would be up to 100 GeV, upgradable to 140 GeV. So just to give you a sense, Hera was about 320 GeV. So the energy of Hera was about, you know, 2.5 times greater. Okay, so it doesn't compete with Hera in energy, but it has polarization, it has ions, and it has much higher luminosities. So it can also do nuclei, and so on. So I had a plot this morning which showed the different designs of Brookhaven and JLab, but as a sign of progress in the field, I'm not actually allowed to show you that, okay, anymore, because now we are down, the Department of Energy in the US is taking a decision that they're going to go ahead in seriously looking at this project, and as a result, no one at Brookhaven or JLab can show slides comparing the two facilities. Okay, so I had things like ERIC and EIC on my slides. I took them, I mean, or JLIC or whatever, so I took it all out. It's just going to be EIC. I should also mention that there's a project in Europe which is further along in terms of further away, which would be like a really high energy machine. It's 4 times that of Hera, but my understanding is that the luminosities will not be as large as the EIC, and it's not clear that they can do polarized protons, though they can do nuclei. So if you are interested in some of the things that can be done, I advise you to look at the EIC white paper. Some of my colleagues and I, we put out this document, you know, almost a couple of years ago now, which also adds to some of the things that were not discussed here. But let me discuss them in the remaining time that I have. So this is time including questions or no, excluding questions. Okay, so I have about 6 minutes and 37 seconds. Okay, so So I'll try and see what I can do. So, so what can this EIC do, right? So I said all these problems, right? So the spin, the distributions, and so on. So what can you do with an EIC, right? You have to tell me what you can do. And so based on our studies, so here's something called the G1 structure function, okay, which measures the helicity distribution of quarks and the protons. So if you have longitudinally polarized photons and longitudinally polarized protons, then the helicity distribution can be taken by flipping one relative to the other. So it's a difference between the proton being aligned along the helicity of the photon or vice versa. And from that, you can extract this object called G1. Okay? And in QCD, G1 is the helicity distribution. Okay? It's the difference, the helicities of the quarks in one direction or the other relative to the proton. And that's related to the spin carried by the quarks and the proton. It's the integral over x of this G1 structure function. If you want to look at the gluon distribution, gluon helicity, just like you heard in the lectures in the last few days, you can understand the gluon distribution in terms of the Altair-Parisi equations for polarized protons, and that's the differential of G1 with respect to Q squared, and that's delta G, okay, the helicity distribution. Now, here's the world data, okay, until EIC will turn on. Okay, so very, very little. Okay, and here's all the additional data that EIC will provide in X and Q squared. The yellow represents our understanding of using Altair-Parisi or DGLAP to extrapolate into these regions. So as you see, if you take this data and you use DGLAP to extrapolate, the uncertainties grow. So when you go to small x and small q squared, your uncertainties just explode. Okay? So what EIC will do is it will actually provide you data in all these ranges, so those bands will just shrink. Okay? And here's a dramatic illustration of this. So this is delta G, right, as a function of x for a fixed q squared of around 10 GeV squared. And this is the current uncertainty based on the world data, which is shown in this triangle here. And what EIC will do is essentially make this very, very small. Okay? So it will really reduce these uncertainties. What does that mean? Okay, so here's a money plot. So this is the current data, okay, on the integral of delta G as a function of x q squared. So this is delta G as a function of delta sigma. So this is the gluon helicity distribution in the proton versus the quark helicity distribution in the proton. And you see that the gluon uncertainties are much bigger, right? So the gluon uncertainty is all over the place, like as I was saying, while the quark uncertainty is smaller. But what EIC will do is it actually reduce it to this very small point. Now, you can ask, how does this constrain the angular momentum distribution? Remember, the spin of the proton is the sum of the spin of the quarks, the spin of the gluons, and the orbital momentum of the quarks and gluons. Okay. So that's this 1/2 minus this, okay? That's plotted here for different x ranges. And you see that it's going to nail it down to this very, very small window here. So if you do the EIC, the promise is that one will actually be able to put a number to what the angular momentum distribution of quarks and gluons is inside the proton. And that's a really non-trivial, profound thing. Okay? So this is really one promise. The other is that we can do 3D imaging. So just like you do, nuclear magnetic resonance tomography, right, NMR, right, you can ask these questions in QCD. And here's a plot of the Sivers function that I mentioned, which is if you look at quarks inside a proton that's polarized this way or the opposite way, the difference of that distribution, that's something called the Sivers function. And the Sivers function is very interesting because it's directly proportional to spin-orbit effects. So just like, in your quantum mechanics courses, you studied about the spin-orbit interaction in atoms and molecules and how they're important, right, in understanding the structure of atoms and molecules. The spin-orbit interaction is absolutely crucial. So you can ask similar questions about the spin-orbit interaction, and that's, the sieverts actually captures some of that physics. And so here's a plot, for example, of in a polarized, transversely polarized proton, what the up quark distribution and the down quark distribution is as a function of kx and ky, the two transverse momenta. So from EIC, in principle, one could extract such images. Okay? And this would be really 3D images of the quark-gluon structure of the proton, which are very non-trivial. And there's some very interesting things related to interference, Arnold-Bohm type effects, just like people in quantum optics talk about, which one could learn through interferences in gluon exchanges in the Feynman diagrams that contribute to our understanding of the Sievert's effect. You can now look at these generalized parton distributions that I mentioned, DVCS, where you measure a photon, and then the proton is put back into the hadron. You can do that of nuclei, actually. You can take quarks and gluons out of nuclei and put them back in, okay, and study their spatial distribution. So you can do very high precision spatial tomography. So this is showing a plot of the distribution of gluons as a function of impact parameter, okay, inside the proton. And you see the thickness tells you the uncertainty band. So you can start asking questions about where the quarks and gluons are sitting near the center or the edge. Okay? Now, you'll immediately see that this has something to do with confinement. Okay? So this is, again, coming at the question of quark and gluon confinement from a different direction by providing you with more information to make models of what the confining dynamics of quarks and gluons are inside protons and nuclei. So these GPDs are absolutely critical, and they lead to this construction of Wigner functions that I mentioned in the structure. Yeah.
Is it possible to measure this, whether it's the distributions of quarks and gluons are more localized at the center of a nucleon or outside? How well can you?
Well, I mean, in some sense, that's indicated by these. This is the uncertainty band in the precision to which. I mean, of course, these are projections based on some particular simulation and so on. But in principle, one should be able to know that quite accurately, I would think. You can also do things like chromodynamic lensing, which is similar to what people in heavy ion collisions call these V2, where if you have a spinning proton, and then you look at this GPD, so you have a polarized quark now put back into the proton. Then there's a coupling again between the spatial location of the spin of the quark and the momentum of the hadron inside, or inside the hadron. So there's a kind of lensing effect that also can be extracted from such measurements, which is very interesting. So nuclei, remember I said we know nothing about the gluon distribution in the nucleus. So this is the current uncertainty, even after all these years, of the nuclear gluon distribution. Even valence quarks there's considerable uncertainty. So this is what the IC would do. Okay? It would really nail down the uncertainty in the gluon distributions inside the nucleus. And even at large X, it would provide new information into the nuclear gluon distribution. Okay? So you're talking about factors of 4 to 8 reduction present uncertainties. And remember I said in hadronization, how quarks and gluons become hadrons. Okay? We don't understand that. So when people do perturbative QCD calculations, they put it into this box called fragmentation functions. Okay? And that's a really fraught thing, okay, at some level. We only understand that in some four-man way. I mean, even the RG equations for that, I find actually somewhat problematic. They're in momentum space, they're not in coordinate space. So it's sort of a non-local kind of OP in that sense. So it's a very non-trivial thing. And so the EIC is going to be fantastic that way because you have this nuclear laboratory and you can ask questions, whether you can ask things about how do quarks lose energy inside a medium. Okay? Are there interference effects that suppress the energy, like the Landau-Pomeranchuk-Migdal effect? So there's, and the other thing that's new about the EIC is that you can also look at, D mesons and in principle bottom as well, and study how they vary with the fraction of the energy of the quark that's carried by the D meson, the pions. So these are very highly precise experiments. experiments. Now, in PA collisions and PP collisions and AA collisions at BRIC and LHC, people do measure energy loss and things like that, or interpret things in terms of energy loss. But the difference with EIC is that you have a finely calibrated probe, okay, on each end. So you know exactly where this object is hitting in the nucleus, whether it's inside or outside, and even possibly the spatial location. This is my favorite subject, which is diffraction. Okay, so at Hera, 20% of the cross-section is due to diffraction. You can go to a perturbative QCD talk, and not hear a word about this. Okay, it's 20% of the cross-section at Hera. And it's a magical thing, okay? So what it's telling you is that at Hera, if you think in the rest frame of the proton, okay, the energy of the electron that's hitting the proton is 50 TeV, okay, 50 tera-electron volts. And what the data is telling you is that in 1 in 7 events, nothing happens to the proton. Okay, the electron blows up, but the proton remains intact. Even though the typical energy, the constituents inside the proton are hundreds of MeV, right? Nothing happens to the proton in 1 in 7 events. And that's because you have this beautiful thing in QCD, which is you have colorless exchanges between the proton and electron, which cause the proton to remain intact, while causing the electron to fragment. Okay? And this is really quantum mechanics at its most beautiful, okay? Because this is a purely quantum effect. And classically, you would never predict something like that. And you can understand this very much in the sense of wave optics, classical diffraction, okay? Where you have, your double slit experiment or something. So you can think of your electron as fluctuating into various Fock states, right? So an electron can be electron in a virtual photon, or it can be a virtual photon QQ bar G, all different Fock states, and they come and they crash on the proton, okay? And they reconstruct themselves on the other side of the proton. And so you can really see patterns, just like you do in optics, of what the cross-section looks like as a function of momentum transfer, and you see this very nice kind of Fraunhofer diffraction pattern. Okay? And you can try and interpret these minima in terms of the various partonic structures that you have inside the proton, or nuclei. Okay? And there's very interesting arguments about the pattern of these as a function of the invariant mass that you have. So these are interesting details of different predictions from QCD-based theories of what would happen. And in particular, this gluon saturation phenomenon that I mentioned is very sensitive to such diffractive patterns, and you can easily separate on day one with the EIC different models of gluon saturation from each other, or no saturation with such pictures. And finally, this is something that I've been working on recently, which is there's some remarkable connections between QCD and gravity. There's some mathematical equivalences between a color memory effect in QCD that is satisfied by these saturated gluons and gravitational memory. That is, this high density regime of gluons in QCD can be thought as effectively like asymptotically free kind of regime of gluon fields, which have memory effects which are exactly analogous to gravitational memory. And if you're interested, I recommend you do this paper. Also, there's some remarkable possible connections between saturated gluons and ideas which describe black holes in quantum gravity as bound states of highly occupied gravitons. And so there's some interesting analogies there that one can understand, explore. And finally, there's something very powerful and quite remarkable, which is that you can understand gravity. So if you compute gravitational scattering, for example, you can understand that in terms of really like the square of QCD. Okay? So you can write down a gravitational amplitude and break that into something that looks like a QCD amplitude times some kinematic factors. So this is some interesting stuff that one can explore. So recently, the EIC received an endorsement. Okay, so it's like a like a stamp of approval. Right? Okay, now now you're good, okay? And so the National Academy of Sciences in the US, they had an endorsement of this project. And here the three key questions that they identified is how did the mass of the proton arise through quark-gluon interactions? How does the spin rise? And what are the emergent properties of dense systems of gluons? So this is, so I'm at 0 time. And so I'll just conclude. So here's the end of my 4-act play. And what I would say is that our knowledge of the fundamental structure of matter is clouded by the vast fog of our ignorance. Though there are bright gems like perturbative QCD and what we learned from the lattice that shine through, that tell us that we're on the right path. At the heart of the matter, right, is the confining dynamics of QCD, and this is the many-body dynamics where gluons play a lead role. Addressing this requires deep and varied knowledge, like I argued. Okay? You can't just sit there and try to prove QCD. Okay? And EIC enables unique and unprecedented measurements. And the history of deep elastic scattering informs us that surprises may be anticipated.
Thanks, Raju, for this beautiful talk. And questions, please.
Thank you. Could you please comment a little bit more about this color memory and gravitational memory? What exactly is this? I've never heard of it.
Okay. Yeah. So let me just talk about the gravity side first. So you all heard about gravitational waves, from black hole mergers and neutron star mergers. Right? And so usually you think of that, and so you have detectors like LIGO, right? And they see this interference pattern that comes when, so there's a phase shift that is measured by these detectors. But what is talked about less is that there's something called a gravitational memory effect, which actually results in an explicit displacement of the detector. So in principle, in addition to when the gravitational wave passed through LIGO, it should actually cause actual physical displacement of the detectors, which would last. Okay. But the effect is too small, okay, and there are lots of factors that make it hard to observe. Okay, there's seismic effects and so on. In fact, there's a huge enterprise now to try and build these things in space so you can actually detect gravitational memory, which is this physical displacement. And it's deeply related to some of the asymptotic symmetries of gravity, okay, so-called BMS symmetries. It's Bondi-Metzger-Sachs symmetries of gravity. Now, a year ago, Andy Strominger and his students suggested that there can be something similar in QCD. That is, if you have Yang-Mills theory, then you can reformulate Yang-Mills theory in such a way that which has an exact analog to this formulation of gravity, so it's exact mathematical analogy. But naively, you would have thought that this is never going to be relevant because, of course, QCD is confining. It's not like gravity. It doesn't have, long-range interactions and so on. And by the way, there's also speculated there's electromagnetic memory in QED, which is a more robust analogy in that sense. But with color memory, the new element that we realize is that if you are in this regime of very high density gluons, where you have this emergent scale, the theory in that regime is really like a classical Yang-Mills theory, okay, which is weakly coupled. And so there, you can exactly identify the transverse momentum kick that you get by, a quark-antiquark pair scattering off these very dense sheet of gluons as the exact analog as a physical displacement of the detectors that you have in gravitational radiation. Now you can say, well, okay, that's cute. What does that mean? So this actually means that you can start to think about these phenomena in QCD in terms of these asymptotic symmetries, which are a very powerful way to formulate the problem. Okay? So you can use conformal symmetry and so on to try and think about these things. So it's not clear that, I mean, it's where it'll lead to, okay? It's still preliminary, but it's possible that reformulating QCD in that language in this particular regime might lead to some insight. And it already has, I would argue.
Is this somehow related to ADS-CFT or?
None at all.
Okay. Thank you.
This is about the spin of the proton. So like if you take the analogy of quark masses, then the quark mass inside a medium is quite different from the asymptotic limit. So I mean, is it physically possible that one can think the same way for the spin? I mean, when the particle is inside a medium, then there is effective different spin degree of freedom rather than the individual particle?
Absolutely. I mean, in fact, I mean, as I mentioned, and I think the use of the word emergent, okay, is a code word for what you just said, okay? In the sense that all these things that we think of as fundamental properties of the object, you know, the spin, the mass, okay, have to be in some sense the emergent properties of the many-body dynamics, right? I mean, the mass, right? The quarks, they carry very little mass. So it is coming from these many-body interactions. So the challenge to me, okay, so what I want to do as a physicist, okay, is to have this built by my friends, okay, I'm not going to build it, and look at this data and try to build a shell model of the proton, okay? In other words, what is a shell model? The shell model tells you that you have this nuclear force, okay, but it's not, you know, the nucleons have their own interactions, but somehow you can think of all the nucleons as moving in this well, okay, in these beautiful shells around in nuclei, and which is a very powerful paradigm, right? And so the question is, can one formulate such an emergent description of these fundamental, quasi-fundamental features of the theory? So I would like to understand the spin and its angular momentum, just as one understands these objects in the shell model of the nucleus. Okay? And that is the ultimate goal, is to arrive at such an emergent description. Otherwise, why are we doing what we're doing, right? So, okay.
My next question is about this QCD square, gravity and QCD squared amplitude. So in this case, the gravity is considered as a pure quantum theory of gravity, or it is a semi-classical method where the graviton is quantum fluctuation on top of a classical background?
No, this is a quantum picture, purely quantum. But it's a symmetry of tree-level amplitudes. Okay, so I stand corrected. So if you're really looking at tree-level amplitudes, okay, in QCD and gravity, you can make this connection. Now, I'm not familiar with whether this is true at higher orders as well.
Yes, so do you expect a production of QGP in the electron ion collider? Because earlier high multiplicity PP collisions were not expected to produce QGP, but I think there is some indication of it.
Yeah, I think it's still a question of debate. I think what one should ask in that sense, what do you mean by QGP? Okay, if you say, do you form a thermalized system, you know, in the sense that is on the lattice with some entropy that is simply proportional to temperature, which is described entirely in terms of extensive quantities, then my answer would be unlikely. Whether you say, if you say, can you produce states which are many body states which are strongly interacting, then the answer is likely yes. Okay, so it's a question of how you form. So it's not clear at all that when you say, okay, you formed a QGP and PP collision, what do you mean? Okay, I mean, you can say, well, I can describe it in terms of hydrodynamics. Okay? But hydrodynamics is a very general thing. It's the long wavelength, late time limit of any quantum field theory. Okay? You have to be more specific than that to say what the nature of that matter is. And so I would say that, But the short answer is I would expect to create dense states of matter with very high luminosities at a DIC. But again, the interesting thing is, and here's an analogy that you might find interesting, is that if you take when you do deep elastic scattering, you can take the photo production limit of deep elastic scattering. And photo production is like a rho meson hitting the proton or nucleus. So there's a limit of deep elastic scattering, which is like PA or PP scattering. And you can do exactly the same kind of analyses that you do at the LHC or at RIC in terms of these multi-parton correlations and trying to understand them in terms of things like flow and so on. But now at the IC, you can dial up Q squared. Okay, so then your object, the projectile, is getting smaller and smaller. And then you can ask, what does it mean if you see these patterns?
Okay, so I see no more questions, and Raju is here, so you can always bug him. And thanks a lot, Raju. We go for tea.